A very warm welcome to today's video lecture series, which will be covered for Module 5, and the lecture number is 49. It is the continuation of the introduction to analog to digital conversion. I, Professor Prasanna Kulkarni, working as Assistant Professor in the Department of Electronics and Communication Engineering from KLS VDIT Haliyar, is presenting this video lecture series. The contents covered in the previous lecture have focused upon the details of analog to digital conversion basics and their various applications. Also have discussed the types of analog to digital converters available in the market, and also we have focused on a particular chip called as 0804, which is used as an A to D converter IC. The learning outcomes after going through this lecture series, the student will have a better understanding of the need of ADC block in every signal processing aspects of electronic design. The contents covered in previous lecture series have focused upon the introduction to stepper motor and programming using assembly and C-level language, and we have gone through the introduction of ADC. And also focused on the step angle for rotation of stepper motors in the previous video lecture series. This present video lecture series will be of level L3 as per the Bloom's taxonomy levels, wherein after going through the basics of ADC, we are able to convert those ideas into the problem solving capabilities to be imbibed in making up the design of ADCs with real-time application, and also interfacing an ADC IC with 8051 for understanding a real environment analog signals to convert them into the digital understandable pattern for processors and controllers. The first one to understand is about the self-clocking method used for ADC. As we have seen in the previous video lecture series, the two important pins called as the clock R and clock in have been connected to 10k ohm resistor and 150 picofarad capacitor, which will give you a time constant function as 110 microseconds. It means analog to digital conversion will be having a conversion rate of 110 microseconds minimum for converting, and therefore if you want to convert this or you want to reduce this conversion time, then this clock in and clock R needs to be used with the external clocks. And when you want to connect an external clock to this, the method is now called as the self-clocking. So through this method, it is possible to reduce the conversion time for the industrial level applications, wherein whenever the rate of conversion is a matter for electronic design, this particular self-clocking method is adopted. And also the need of clock for analog to digital conversion is a major question, that why we need a clock for conversion. So the answer for this is that whenever we do the sampling of analog signal converted to digital signal, we need proper time stamping. That is how the sampling rate needs to be kept constant. The variation is not acceptable. Therefore, we need to have a time scale that after what time the analog signal must be sampled, or in other way it is to be encoded with a new value, and that is called as the time stamping. So therefore, to maintain this particular time of sampling, we need a clock frequency. This clock frequency will keep a track after what time the analog signal needs to be sampled, and therefore every analog to digital conversion ICs needs a clock as one of the important functions. I think now everybody have understood why these clock frequencies are used for A to D conversion, and also what is the advantage of using this self-clocking method. So the only difference we will see here is that all of the internal connections will remain as it is, such as RD bar, WR bar, INTR, which are very particularly connected. You can observe that pin numbers which are used, okay, they are very particular. But only for clock in and clock out we use a external frequency for interconnections, and this is what called as the self-clocking method used for ADC 0804. Now there is one more concept, okay, using an external clock frequency in my next slide. This is a connection diagram which will show you how can we adopt that instead of using a clock from external frequencies, can't we use a clock of 8051 itself? And this diagram will show you a brief connection. How can we use the crystal clock available for 8051 used for the ADC 0804? Now you can observe some minor changes which have happened. That is, the clock in and clock are now not connected by a resistor and a capacitor. Instead of that, the clock R is made open and clock in is now connected by a output of D latch or D flip flop. So you can observe that the original crystal frequency of 8051 is divided by 4. It is divided by 4. So each latch will divide the frequency by 2, by half. When you connect the subsequent output of the first latch Q as a input to the next one, or it is connected as a clock to the next one, it obviously means that when Q produces output, only then the next latch becomes operated. Or in a simple way, when the crystal 2 is connected to first latch, when the rising edge occurs, because it is a positive edge triggered D flip flop, when the positive edge occurs, only then the Q will be produced. And the similar way, this Q becomes a clock for the next latch. It means that when the positive edge of Q occurs, only then the output of the second latch will produce the value on Q, which obviously means that frequency is downscaled, and in this particular diagram it is downscaled by 4. So the crystal frequency is divided by 4, and that frequency is used as the clock in frequency for ADC 0804. It obviously means that your conversion time is very much reduced. So in this diagram it has shown you how this ADC 0804 can be used with respect to the internal clock frequency of 8051 to increase the conversion, to reduce the conversion time or to increase the speed of ADC. I think everybody have understood this diagram very clearly. Now let us go into the next particular chapter, which will also focus upon the programming concepts. Examine that ADC 0804 connection to the 8051 as shown in the previous figure. Write a program to monitor the INTR pin and bring an analog input into register A, which is accumulator. Then call a hex to ASCII conversion and data display subroutines, and do this continuously. Okay, so these subroutine programs can just be called. Okay, no need to write those subroutine programs separately, just you need to call that subroutine program. Okay, so before we write a program, first of all we should know the IC of ADC 0804, what all important pins that it has got. Okay, so therefore initially in the program I have made that listing. So 2.6, pin 2.6 is called as WR. Okay, now till now I think if you have gone through my previous video lecture series, now you understood what is WR. WR obviously means that it is a start of conversion, that just now an analog input has entered and I have started converting it. That is the meaning of WR. Okay, and this needs a low to high pulse. So in my program I need to generate a low to high pulse for WR, which is connected to pin P2.6. Similarly 2.7 is INTR, okay, which is low, it means it is end of the conversion. So INTR goes low, which obviously means that the conversion has been completed. So two important things. The start of conversion is indicated by WR. The end of conversion is indicated by a low pin, and that low pin is INTR pin. Done? Okay. So pin 2.5. 2.5 is called as RD. This needs an high to low pulse, will read the data from ADC. So once the conversion is completed, that is when INTR goes low, which means that the analog data which is entered is converted to some digital value, and now you are able to read it. To read the data, I have to assert an high to low pulse on pin P2.5, which is called as RD. Only then data becomes available. Now how do you read the data? So pin P1.0 to 1.7, that is entire port 1, is used as data line of ADC 0804. So if you know these ideas, definitely we can write a program as what I have written in the next lines. So let us go through this. Move P1, has 0FF. This will simply make your port 1 as an input port. It will act now as an input port, that is P1. P1 port will act now always as input port. Then clear P2.6. Now what exactly you are doing? 2.6. In other words, you are making it low. Okay, because you have to start the conversion. So initially that line has to be low. So therefore I am forcing that P2.6 becomes 0. Now to start the conversion, what is the next pulse? I need to apply high pulse. How do I make it high pulse now? By setting that particular bit. So set B P2.6 will make that WR pin to become 1. Now this has successfully made low to high conversion pulse. It means now I have asserted the WR pin. Now you are ready for conversion. That's the meaning. Next one, JB 2.7, comma here. So once your data is asserted, what is my next job? I need to wait till the conversion is completed. It means ultimately I am waiting for INTR pin to go low. And unless it is at high, I should keep on waiting. So therefore I use the instruction JB, jump if bit is set. So until it is in set position, I have to be in the same line of code. I will be in the infinite loop until that P2.7 becomes low. So once this becomes low, I will be coming out of this loop and I immediately go to the next line. What is my next line? Clear P2.5. So when you know that the INTR pin has gone low, it means the end of conversion is done. The meaning is that data is ready. But to make it available, what you have to make? A high to low pulse to be generated on P2.5, which is called as RD. So what I have to do now? I have to make that P2.5 clear. So clear P2.5, which means that conversion is finished and your RD is ready. So you have cleared that pin P2.5, which means that RD is made 0. Once this is done, what do you mean by this? Your data is available on port 1. Now how to read that data? Using simple move instruction. Move A, P1, because in the program statement it was told that the data has to be copied to register A, and therefore now in register A the data is copied. Now after doing this, we need to call for a subroutine. Okay, here we are not writing a complete program, just we are calling subroutine as a call conversion. Conversion is a subroutine name which will do hex to ASCII conversion. This we have done already in module 2, how to convert an hex number to ASCII. So the same program can be called as a subroutine program here. So I will not be going to that part in this particular program now. Second one, after completing this, second one is displaying the data. So already we have finished LCD program also. So therefore I have not again written the same program repeatedly. Simply I write a subroutine name, call data display. So display the data on the LCD. Whatever conversion you have done it, display that data. So once I do this, what is my next job? I have to make RD to become 1. If you don't make it 1, it means that every time you will read the same data, you will not get next data at all. But to get the next data, I have to make my RD pin, again it should be set to 1. So therefore, I will make set B P2.5 and RD becomes 1, and then whatever next data comes on analog channel, again it is converted and the data becomes available. Then RD pin, because it is already set, now only I have to make it reset it and data becomes available on port 1. This is what a job of an analog to digital conversion, and this is to be done continuously. Therefore I use a short jump, go to back as a label. I think everybody have understood what is being done. These are some basic fundamentals. Okay, if you know about the operation of these 4 pins, namely WR, INTR, RD. Okay, if you know about these 3 pins and data is available on port 1, if you know these 4 facts, then you can write program for ADC 0804 in a very simple order. Okay, so let us see some more programs on this one. That is what writing 8051 program in assembly. Same thing, I want to do it in assembly. Then how to do this? So I assign the port with a name. So my data EQU, okay, P1. It means henceforth port 1 is referred by a name called as my data. So make first that an input port. How do I do this? Move P1 comma hash 0FF. By default P1 becomes an input port. Set B P2.7. Set B means what it is now? INTR. You are making INTR initially 1. Then clear P2.6. What is that? Clear pin is nothing but just refer to the previous. If you have not understood this, clear P2.6 what? WR. So WR pin you are clearing it, and then you are making it again 1. So you are converting, a conversion is happening. And then what is your job? Is to check the status of your INTR. So how do I state that status? JB P2.7 here. So you are monitoring this whether it is becoming 0 or no. It's already 1. Okay, you are verifying whether it will become 0. And when does it become 0? When the data conversion is completed. Okay, so therefore initially I forced that pin to become 1. I waited that it should be made 0 by conversion. After conversion it should be made 0. I am waiting for that conversion to happen. And then I will clear P2.5. Now what is 2.5? Anybody knows it? Yes, it is RD pin. Very correct. So clear that RD pin 2.5. Then move your data. Move A comma my data. My data is nothing but your port 1 copied to accumulator. And then you should set it back. RD has to be again set back. Without that you don't get next data. Same previous data comes on to accumulator. I don't want that. Next data I want it. So therefore set B P2.5 and short jump back. This is a very simple fundamental, and that's why I write a program for ADCs also in simple assembly level programs. Okay, so let us go to another type of program, writing in C level also, because we should be having both the skills. I should be capable of writing assembly programs also. I should be capable of writing C programs also. But the important fact remains always the same. That is, the basics will never change. For every engineering subject, it is to be understood. Whatever the new advanced subjects may come, but the fundamentals will remain the same. And for every engineer, the fundamental is a must. If you know your fundamentals, then absolutely will not have any problems to learn any advanced methods comes in. So let us come back to the program also. A hash include RG51. We have added a header file, library file also for us. Then I need to set some bits. That is S bit. S bit is a data type used to declare. RD is the name of the pin. I am going to refer it, and the pin I am going to assign is 2.5. For WR I will assign 2.6. INTR I have assigned 2.7. So keep the pins same so that you will not have any confusion. Keep them same. Next one is SFR. Please remember this. I cannot use S bit as a declaration because S bit is single bit, whereas port 1 is not a single bit. It is a 8 bits. So therefore I have to declare it as SFR only. SFR my data P1. Then void main is a function called, then unsigned character value. I will be using a variable. That variable name is value. And initially I do my data is equal to 0x0f, means making port 1 as an input port. Then I will make INTR 1. Initially I will force that INTR should be 1 and RD should be 1 and WR should be 1. Initially I will force them that initially they should be 1. Then I write infinite loop while 1. While 1 is called as infinite loop. Next, what I do? WR is equal to 0, okay, and then a delay. After that delay, WR is equal to 1. Okay, so I am creating that low to high pulse on WR. Then what I have to wait for? INTR. So I will use a loop. I will use an instruction as while INTR is equal to 1. Till then, okay, while I should be in the same iteration while. Once INTR becomes 0, then I am free to do. What I can do very simply is that value is equal to my data. If INTR continues to be 1, then RD will be at 0. Then RD will be at 0. Understood this point? Okay. And then I get a value. Value is equal to my data. So whatever is on port 1, that will be stored in the form of value. And then I set RD is equal to 1. So it is a C program what has been written. So but the fundamentals have remained the same. What all I have done in assembly, same concepts are written in C but with the help of operators. because C will support you ready-made operators for ourselves. So therefore was some minor changes only in writing, okay, syntax level, but the fundamentals have remained the same. Pins have not changed, okay, the same pins are being used. I'm monitoring the same pins also. So please remember that ADC, if you know these 4 facts what I've explained, then it means that you know the program for ADC 0804. I think these 3 programs have given you a sufficient idea to understand how to write a program for ADC interface done with 8051. So my next topic will be to discuss another chip called as ADC 0808, and the advanced version is also called as 0809. Okay, again this is one of the fantastic chips when you compare with 0804. Okay, the comparison between these 2 chips according to me are, this 0804 is meant for only single analog channel. Okay, you don't have multiple analog signals sent to the IC. You can send only one signal at a time. Okay, one signal at a time, and only one channel is available for reading the analog signals. Okay, but in 0808 you will have 8 different channels. It means in 0804 you can connect one sensor, but in 0808 you can connect 8 different sensors. 8 different sensors. That is the capability of this 0808 chip is all about, and it is having some fundamentals. Pins have been changed. There what we had RD and WR have been changed in 0808. That I'll explain in this slide also. Okay, so I think the major difference is this. Fine. Next, this ADC 0808 has 8 analog inputs named as IN0 to IN7, as in the diagram which is indicated, IN0 to IN7. So 8 inputs are available, analog inputs. You can send 8 analog signals to this pin. It allows us to monitor up to 8 different transducers using only a single chip. That is the advantage of this particular chip is all about. Okay, so this is a multifunctional where you have multiple sensors, multiple transducer connected, and you need to convert them to digital. And if you want to do the job of this by using 0804, you need 8 chips, 8 different ICs to be connected. But this entire 8 chips can be replaced by one chip, that is 0808. I think you have understood now what is the capability of this particular chip is all about. Next, the chip has 8 data output just like ADC 0804. The output here are D0 to D7. So there is only one output channel available, whereas 8 analog input channels, but there is only one output channel. Okay. Then the question obviously may come, if there are 8 inputs and there is only one output, then how do input channels are recognized, or who will get a priority? For that also there is a solution. Okay, just like a multiplexer. That as in for a multiplexer we have a selection lines. Based upon the selection line, the particular channel is selected. The same fundamentals are used even in this particular chip also, that there are 3 different selection lines named as A, B and C, and C is treated as MSB, B is a middle bit and A is LSB. So therefore the series is written as CBA. C is MSB, B is the middle bit and A is LSB. Okay, this is how the series is used, and because of this multiplexing inputs are available, you can select a particular channel. Just to give an example for you, suppose I make CBA as 000. It means that you are selecting channel number 0 or IN0 according to your chip diagram. Okay, and if you are selecting CBA as 011, then which line will be selected? CH3, channel 3, or according to you, I think this is now IN2 will be selected for your chip selection. Based on, just like it is a multiplexer, based upon that selection line, a particular analog channel is selected and the conversion will happen and the digital output is produced. It means that you cannot read all the 8 analog channels at the same time. Okay, you cannot read all of them at the same time. Based upon the selection, you can read this particular transducers or sensors available to it. Okay, the pin details are as configured. Now I will highlight some important chips signals over there. I think ground, okay, clock is the input clock that has been used. Then VCC, it uses again plus 5 volt of supply. Now important ICs chips available for us are SC. SC stands for start of conversion. Okay, and it is sometimes it is also called as SOC. SC and SOC are replaceable words here. Start of conversion. Okay. Similarly, EOC stands for end of conversion. Okay, so it is exactly replacement. You can compare this: start of conversion, end of conversion. So whenever the data becomes available on analog channel, the start of conversion pulse has to be raised, and when the data is completed, conversion is completed, EOC will be raised, end of conversion. Okay, right. Similarly, ALE, address latch enable, because you have to select the particular channel. So therefore an ALE pulse is also used, as just now I have spoken, CBA, or nothing but data selection lines. Okay, then OE stands for output enable, and please importantly focus that SC is an input signal, ALE is an input signal, all CBA are input signals, then OE is also an input signal for this chip. There is only one output channel called as EOC, end of conversion. These are very important points as far as the programs are considered. When I write a program, I should be knowing which is input signal and which is an output signal. I think the chip is now very clear to all of you. Now let us go to some more understanding about this particular chip and how to write a program on this. What are the steps that we need to follow? Okay. So ADC has 8 analog channels, as just now we have discussed. So you can monitor up to 8 different transducers using only a single chip. That is what advantage we have. And this chip has 8-bit data output, just like ADC 0804. Okay, and the selection channel will be like this. Like example, 000 IN0 will be selected, 010 IN2 will be selected, 011 IN3 will be selected, 110 IN6 will be selected, 111 IN7 will be selected. So based upon this, you can select a particular analog channel and the conversion can be done with from analog to digital. So this is the channel selection table available for us. Okay, now let us go to the steps for programming. How do we write a programs for this one? Okay, so these are very important points as far as the programs are considered. If you follow these things, writing a program will not be so difficult for us. Okay, first thing, select an analog channel by providing bits to A, B, C addresses. This is the first thing we do. We have to select which particular sensor line or a transducer line I am referring for. That is to be done. Second one, activate the ALE pin. ALE is nothing but address latch enable. How do I activate this? It needs an low to high pulse. So 0 to 1. Okay, rising pulse. You can remember ALE needs a rising, that is 0 to 1 pulse to latch the address. Address means what? ABC, which particular line that you want to read. That is called as ALE. That is job of ALE pin here. Third step, activate SOC, or it is also called as SC start conversion. Okay, and this needs an high to low pulse. So 1 to 0 pulse is required to initiate the conversion. So 1 to 0. Okay, then end of conversion to see whether the conversion is completed or not. Your job is to only monitor because it's an output signal. Please remember this. Okay, I need to only check whether it is in EOC is finished or not. Fifth step, activate OE, that is output enabled, to read data out of the ADC chip. So OE to read the data from the chip will happen after EOC is done. Once end of conversion pulse is generated, then only I should be reading the data, and to read the data I need to activate OE. OE stands for output enable. Okay, and to do this job I need to send a high to low pulse for this. Okay, ALE low to high, start of conversion high to low. You should only monitor EOC. Next one, once the EOC is completed, OE to be activated by sending H to L pulse, and then the data becomes available on the output channel, just like your ADC 0804. Did you remember these steps? If you know these steps, then you will understand the program. If you have not understood, please read this once again, try to listen to this once again, and then come to my program. Okay, now I want to write a program for this ADC 0808 in assembly level program. Okay, so what all we have discussed, we have to incorporate that into my program. So my data, I'll be using port 1 once again as my input port for us. So my data EQView P1. org, I'm going to write a program starting initialization, then move my data comma has 0ff. So I want to make that P1 as input port, so I have moved ff to this. Then EOC, what is the end of conversion? Okay, first of all I need to set that. Set P2.7 as an input. First set P2.7 as an EOC or an input. Next, clear P2.4, clear 2.6, 2.4 is ALE, clear 2.6 is SOC, start of conversion, all of them are cleared. Clear P2.5 OE, all of them are initially cleared. Okay, and then I will select a particular channel. How do I make a selection now? Clear P2.0, P2.0 you can call it as A line, so A is made 0. Clear P2.1, B line is made 0. Next, set B P2.2, it is nothing but C. So what is the total channel selection now? 1 0 0. Okay, so 1 0 0. Which particular line you want to select is IN4. You are selecting is IN4. That is your input analog channel available. Okay, by this selection line. Understood? So if you change this particular selection line also will change, and you will be able to read the different sensor. Now what is the next job I'm going to do after this? Now what is important? I will call a delay. Okay, call a delay program. Okay, I did not write a delay program, but the delay program will remain the same. Okay, so you can use the same delay programs here also. Next one, I will set P2.4. What is 2.4 here is ALE. I will set it first. Okay, again I will call a delay because everything needs a time. I cannot simply just keep on setting the signals. I need some delay also. I call a delay and then set B P2.6. 2.6 is nothing but start of conversion signal. Again I call a delay, once again. Then I will clear 2.4. You can see that initially it was set. I called a delay. Again 2.6 was set. I called a delay. Now I will clear both of them. P2.4 also, 2.6 also. Means what? ALE job is done. Start of conversion signal is done. My job is done. Now what is my next job is to go for? To check the EOC. To check the EOC. How do I check it? Using a instruction JB. JB 2.7 comma here. So if it is still set, I will be in the same loop. If it is not set, I will go to the next loop. What is that next loop? JNB 2.7 comma here 1. Okay, so the loop has to be broken by one or the other signals, because when it rises, okay, the first signal gets broken, and when it falls, the second loop gets broken. Understood the meaning of this one? So both will get broken when both the conditions are met. That EOC should be high, then it should go low. Both conditions are verified. When both the conditions are verified, I am very much sure my end of conversion is done. Because end of conversion signal is not only rising signal, or it is not only the falling, it is both rise and fall. So how do I check this? Using this particular technique. I am checking for rise also and I am checking for fall also. Both the pulses are verified by both of these JB and JNBs. Once I may confirm that end of conversion is done, what is my next job? Is to make P2.5 set. Earlier it was cleared. How do I set it? Using instruction set P2.5. So if you do this, the meaning is that now output enable is done. Once the output enable is done, where the data is available, it is available on port 1. So therefore, before I call port 1, I call it small delay. Okay, a call delay, so that data is successfully written on port 1. Okay, and from that port 1, my job is to simply copy that to accumulate. Okay, and here only I should not leave it, because output enable you have done it 1. Fine. Again it should be made 0. If you don't do this, you will not get the next data. Same old data gets copied every time. So therefore, I should make sure that that particular pin is cleared. Clear P2.5, short jump back. So you are going back once again, you are selecting again the same channel. That is what it has been done. So if you have understood this fundamentals, writing a program also is not at all difficult. I don't think that these programs are really difficult to write or cannot be remembered, but the fundamentals to be understood. What is the signal, how to be activated, how it should be deactivated, once it is activated what happens, when it is deactivated what happens. If you know these 3 to 4 line fundamentals of this, ADC is nowhere a tough job for anybody. Okay, I think everybody have understood these programs and I have tried my maximum to make you understand the programs. If not, please try to listen to this video lecture series once again. Try to write the programs on your own, try to elaborate it, then definitely I think you will get a clear idea about this ADC programs. Okay, so before the end of this, before we end, let us understand what are the advantages or applications of this analog to digital conversions. Okay, so in the modern world of growing technology, we are very much dependent on digital devices. I think your no day starts without any digital devices. I think every day you wake up by looking onto your mobile phones, which is I think again a digital device. Okay, I think your entire day has been surrounded by some digital devices. So these digital devices operate on the digital signal. Obviously the processing for any digital devices needs a digital value. It cannot take analog data. Okay, definitely it takes input, but it is converted to digital and then it is fed to your device. Okay, but not every quantity is in the digital form. So in the entire universe you directly don't get any digital data. No thing will give you digital value 0 1 0 1. Nobody will give you that, but we want it for our systems. So therefore we need ADC. So for every digital device you see in the world has ADC inside. That is a very simple meaning of this, all these words. Some of them very famous cell phones. I think you are very much fond of cell phones. Definitely all your voice is a digital voice, everything, and therefore original voice is analog, but for a device to process it, it's to be converted to digital. So obviously we need a analog to digital conversions are used even in cell phones also. Similarly, images and videos, you are fond of watching a lot of movies, you are fond of taking selfies, group photos, everything, cameras. Definitely even camera, whatever you take a picture is an analog, but it's to be processed, and for processing we need to convert that image to digital form. Okay, that we call pixel values, and therefore definitely we need a analog to digital conversion even there also. And some medical applications also like X-rays and MRIs, all their inputs as images. Okay, they are all images for us, but it is to be processed, and for processing we need a digital value, and therefore even for medical imaging processes also ADC is one of the fundamental block that the image has to be converted to digital form. Then music, which everybody is fond of listening to, and definitely these also needs a conversion. Okay, modernly they are available in CDs and pen drives, you can easily copy them. Then a digital oscilloscope, I think in our lab also we use the digital oscilloscope nowadays. Earlier we had an analog oscilloscope, now we got digital oscilloscope also uses analog to digital conversions. Now air conditioners, which is a need of today for summer. I think air conditioners very much are required. They have got temperature sensors for maintaining the temperature. Okay, automatically they are set, and they have temperature sensors. This temperature is an analog quantity, so it is to be converted to digital, and then the processor will take that input value, and based upon that input value received, it will take action, whether the temperature to be lowered in the room or it is to be set to some particular nominal values, and therefore that decision is based upon the processor, and the processor gets a data from a sensor, but sensor will convert that analog quantity of temperature to some digital readable quantity. So you can see that this ADC is becoming one of the fundamental blocks in every digital circuit. ADC is a must. I think with this brief applications, everybody have understood what is the need of this ADCs, where all they are used, how do you write a program for them, what are different ICs are available, and I've tried my best to make you understand about the ADCs. I thank you everyone for attending to this video lecture series, and the references what I have been using is Muhammad Ali Mazidi, Jason Gillespie, and the McKinley. Very good book as far as the interfacing are considered, and some for information on ADCs like chip diagrams and all, you can refer to Kenneth Ayala, and or else you can go to Manish K. Patel, also has briefly discussed about this interfacing diagrams, and also Raj Kamal for more interfacing diagrams on this, or having more information on ADC and DAC conversions. I thank you for attending to this video lecture series. I thank you one and all.